Yes, thank you for the introduction. So this is joint work with the other people of the algorithms group in Marburg. And we are looking at a string factorization or string partitioning problem, which is pretty closely related to finding these anti-covers. So let me start with the application, which is nicely described in this paper by Condon et al. And the thing that we want to have in the application is we want to produce a longish DNA string. So we have this double-stranded DNA string, and from a technical point of view, it's easier to produce short strings. Okay, so these are called oligos. So the idea of this oligo design is that you produce short strings and then you hope that they will assemble to the long string. So let me start off with one possible set of oligos here. So we could like create the blue string, then this red string, then this green one, this grayish one, and then these strings on the other side. Okay, and now what you actually produce in this application is you just build these like colorful short strings, and then you hope that they will assemble as wanted in your test tube, let's say. And this assembly, it's because you have these complementary base pairs, right? So that's what drives the assembly. So the idea is just like you have to throw in this, no, that's not the right one, this one. So you just have to throw in this blue one, and then if you throw in the other blue one, they will assemble like this. And then this will continue because we have this nice brick-like layout. This will continue in such a fashion that eventually we will build the correct string, right? So I think this is what it should look like. And now there's a problem with the set of oligos that I designed here. And this problem is that these two are the same, right? And this is what is called a collision in this application setting. Why is that a problem? Because the two are the same. We have that this string not only binds to this one, but also to this other one because it's the same, right? So another assembly that we could have is the following. After we have these first three strings assembled, it could be that this orange one already binds here, and then we just have a shorter string. It's not the one that we actually wanted to produce, right? And so one thing that we have to take care of in this choice of oligo substrings is that they are not too equal, right? And so that's the application. And let's say after a series of abstractions and simplifications, this leads us to this problem that we study in this paper here, which is called equality-free string factorization. And we have our string given, so we only talk about one side of the DNA string now, and we want to factorize it into k factors. So in this talk, k will be the number of factors, not the length of the factors. And we want to have that they are all different, okay? So yeah, one such partition could be, let's say this one. Then they would be all different, right? No two strings are the same here. So this is a yes instance for k equals 4, for example. Okay, if we think about the application, then it's actually not sufficient to just demand that these things are unequal. You would actually want to have like bigger differences between the factors. So motivated by this application, we kind of look at a generalization of this problem, which we called R-free string factorization. And we don't want different factors, we want K factors such that they are not in relation R. R is a relation between strings. We can choose an arbitrary one. It doesn't need to be an equivalence relation. It can be anything that you like. And so this should be, they should not be in relation if they are different factors, right? So if I is not J, right? Okay, so, and there are several variants, concrete variants of this R that we consider in this paper. So one is having the same alphabet. We denote this by this equality with a sigma. So in that case, these two strings, they would be equal with this, they would be equal with respect to this relation. And so they would collide in this variant of the string partitioning problem. So this would be like the equivalence relation where all strings are equivalent if they have the same set of letters. Then another one that we considered was where we consider the parec vectors of the strings. So we count how often each letter occurs. So in that case, these two strings would be different. So this string and this string would be different because the G, for example, occurs more often in the second one than in the first one. And then we considered also prefix relation. So two strings are in relation if one is a prefix of the other one. And in that case, these two strings would be in relation, right? Because the first one is a prefix of the second one. And it makes sense from the application point of view to also forbid this, that one factor is a prefix of the other one. And if you can do prefixes, you can also do suffixes and maybe also substrings, right? So you would say two factors collide if one of the is a substring of the other. Okay, so this is the general problem that we studied in this paper. And there has been, of course, some previous work on this. For more detailed discussion, you can have a look at the chat. There's discussion of these two papers here. Oh, and also this one, the one by Biko and Popper was also mentioned in the last talk. So what is known in this first paper, it was shown that equality-free string factorization is NP hard. And this paper is actually about more general types of word equations, but one result is this hardness of equality-free string factorization. And another known result, which is I think like the starting point of our work, is that you can solve it in this running time. So it has like an FPT algorithm for the number of factors. And the idea of this algorithm is actually quite easy. So let me describe it briefly. Let's say we have this string, so it's only C's. To make sure that two factors are not the same, it's sufficient to have them different lengths, right? So if they have different length, they are not the same. So what you can do if you have a string is you can like have picked substrings of increasing length, and this gives you an equality-free string factorization. And with that observation, you have the following simple algorithm. So you look whether n is larger, the string length is larger than k squared. And if this is the case, then you can directly say yes. You have a yes instance. And if this is not the case, then your n to the k brute force algorithm will be basically O of k to the 2k algorithm, right? So this is this first step, basically dealing with the large instances that are much larger than this k. This is what is called a kernel. So the algorithm is basically just this kernelization. You get a quadratic kernel, and then you can do brute force on this kernel. So this is what is known for this problem so far. And maybe one thing to observe is that this whole approach, it breaks down if we don't have equality, right? If we take, for example, the having equal alphabet as our notion of collision, then this clearly doesn't work, right? This is there's only one factor if all the letters are the same. Okay, so this is what we had before, and now our main results are the following. So we improve the running time from this k to the O of k to 2 to the k, so the parameterized, the exponential part of the running time. And we do this not only for equality-free string factorization, but for R-free string factorization, for all R that are equivalence relations and can be computed in polynomial time. And then we show that this R-free string factorization is NP hard for these variants that we proposed, these new ones. And for this prefix relation, we also show a kernel. So this NP hardness, this is basically heavily borrowed from this paper by Fernau et al. So I will not talk about this. And this kernel, it's a bit messy, so I will also not talk about this. And I will focus on this algorithm in the remainder of the talk. So this algorithm, it's based on a reduction to a graph problem. And this graph problem, it's called rainbow ST path. So we're given a directed graph. I'm drawing a DAG, but it doesn't need to be a DAG necessarily. And you have two special vertices, S and T. And the vertices have colors. So maybe like this. And you want to know whether there's a simple path from S to T such that all the colors are different. Okay. So this is the problem, and we will reduce to this problem in the following way. I will give a concrete example for this short string ACAC. At the one optimal equality-free string factorization. So I will give the example for equality-free string factorization and then discuss why it works for general equivalence relations. So one equality-free factorization would be this, right? A is different from C, A is different from C. Okay, so the reduction is as follows. For every factor or every pair of positions in the string S, we create one vertex, and then we add edges if two vertices can be subsequent factors in the factorization, right? So if we end the first factor ends at 1, then the next one has to start at 2. So we add these edges, right? And then if it ends at 2, then the next one has to start at 3. So we add these edges. this edge, this one ends at 3, so the next one has start at 4. This one ends at 2, so need to add these edges, and then this one remaining missing edge, and this is basically all the edges that model that factors can be subsequent factors in the factorization. Then we add the special vertex S and the special vertex T, and the S gets an edge to all the factors that start in position 1, and the T gets an edge from all the factors that start at the last, end at the last position of the string. And now we have to add the colors, right? And the colors, they are determined directly by the equivalence relation. So this string, this is just the A, and this substring, so which only contains the third position, is also the A. These two are C's, so they get the same color. This string AC, this is the string AC. This occurs also from position 3 to 4, so these get the same color, and all other strings occur only once, so they get their own private color if you want. So that's the coloring, and now we have that factorization corresponds to a path from S to T, and if the factorization has k factors, then this will become a path of length k plus 2 in the graph. Okay, so this is the whole reduction. Note that we can replace this asking for equality by any equivalence relation. We can also demand that the factors that we choose fulfill some additional constraints. For example, we can say we only want to consider factors of length at least, of length at most 2. So in that case, we would simply not add this factor to the graph, this factor, and this one, right? So we would just take a subset of the factors and build another graph. So the path that corresponds to this solution that I showed on the before starting the construction, this would be exactly this path, right? So we'd start at S, then go to the vertex 1, 1, which corresponds to A, then go to the vertex 2, 3, should correspond to CA, and then go to the vertex which corresponds to the last character C, and then we go to the final vertex T. Okay, so this is the construction, and now what remains to do is we need to discuss how to find this path, and you can do that in 2 to the k time by using this narrow C's technique. It's an algebraic technique, and just roughly speaking, what you do is you reduce the path finding problem to a problem of testing whether some polynomial is identically 0 in a field of characteristic 2. And this polynomial, it consists of monomials for the walks, the k walks of the graph, and these. So you have variables for the edges and variables for colors, and then there's something called a label of each vertex. And these labels, this is like the technical part where you make sure that this polynomial is really identically 0 if and only if the instance does not contain a path. And the point for introducing these labels is that all the walks which have some color that occurs twice, they will vanish because of this characteristic too. So that you will have several monomials that cancel each other out. So that's the very rough idea for this. And one other point that we need to discuss, of course, this polynomial is very large. It's much larger than 2 to the k times some polynomial in n, but we can evaluate it efficiently in this 2 to the k times poly n time. So that's the algorithm that we use. It's basically a small extension of what was known for directed k-path. And so let me conclude with some question for future work. We would like to beat this running time bound, not because it's so bad. So this should be good enough for applications actually, but to beat this time bound, you would really need to go into the string structure of the problem, right? So far, this reduction to the graph problem like abstracts away from the string, and to get better, you would really need to exploit the properties of the string problem. Would be also interesting to have like a better kernel for this equality-free string factorization. So the current kernel has like a quadratic size, and it's trivial, but coming up with a linear one is not so easy. And also we would like to have polynomial kernels for these other equivalence relations. We would like to improve the running time bound for this prefix-free factorization, where we have FPT algorithm only, but with a basically k to the order k running time. And the final thing from a theory standpoint would be to show that we have an FPT algorithm for this substring relation. Because we don't have a kernel for that one, we don't have a FPT algorithm. And finally, I'm also interested in looking at exact algorithms, implementations of exact algorithms for this problem. And in that case, probably for more realistic variants than the equality-free string factorization, but maybe some variants where you demand that the factors have like a certain Hamming distance or something like this. And with that, I would like to conclude my talk and thank the organizers for organizing this CPM in this special times, and also thank the other speakers for the nice talks so far. Thanks.
Thank you very much, Christian.